very important inequality when we are dealing with complex numbers, also real numbers, but real numbers is a particular case, is the Schwarz inequality. Okay, and here what we have is two strings of complex numbers, a1 through an, b1 through bn. If you want, you can think about them as vectors, complex vectors with complex entries. Okay, and then what we have is that the sum of these pairs, a1 with b1, an with bn, keep in mind we need to conjugate the b, okay? Otherwise this is not going to work. And then square the whole thing is less or equal than the sum of the squares of the modulus of a's times the sums of the squares of the moduli of the b's, okay? And then that's the Schwarz inequality. Now, just a quick reminder, although I think you know this, but sometimes we have difficulties, right, with handling the sigma notation. So the sigma notation just means when you expand it, that you are taking whatever is inside the xj's and you are just adding all of them together. Okay, that's just a quick reminder. Let's get into the proof of the theorem of the Schwarz inequality. If we want, we can think about this inequality in terms of vectors. Let me just give you the idea. Then we can go into the details. Okay, so these two vectors are vectors in a complex space. Okay. And then what we have as the inequality is that the absolute value of the scalar product of u times v is less or equal than the magnitude of the vector u times the magnitude of the vector v. Okay, notice that the square that was here in the numerator on the left, I passed it to the right as a square root. Okay, that's why I'm not writing it here. Okay, so this is the intuition. However, here there are so many things that we haven't discussed, right? Like I'm talking here about vectors, and I'm talking here about the inner product. All these things we will see later. So this is just to get an idea, but nothing else. Okay. Now, once we have this idea, what the inequality, the idea for the proof is that we have our two vectors u and v. Okay, and these vectors, we can, for example, decompose u into two parts, one that is perpendicular to v and another one that is in the direction of v. Okay. Now, here the key of the proof is that we are going to be keeping just one of these two components, the perpendicular or the other one. And there, you see that there is a less or equal here. So the case of the equality, I give you this hint. The case of the equality is when there is no perpendicular component. The vector u is parallel to v. Okay, so keeping this idea in mind, I leave for you to understand all the tricks that we are going to do now, understand them geometrically. Okay, but the way to think about this proof geometrically is in terms of projections. All right, so having said that, what we are going to do is to look at the very special combination that is b times aj minus cbj square. Okay, and what is a and what is b? So A is the sum of the AJ's square, okay, and C is going to be the sum of AJ BJ modulus, okay, from J equal 1 to N. We will also need capital, yeah, we already need capital B, which is the sum of the modulus of BJ squared. Okay, so these three quantities we need. Now, as I was saying before, think about this quantity I wrote here in terms of the projections into V or the orthogonal to V. Okay, I'll leave that for you to think. But that's what we are doing here. So once you have this idea that in a problem will typically come as a hint, okay, the only thing you can do is notice that you have a modulus square. So once you have that, the sensible thing to do is to multiply the number times the conjugate. Okay. Now the conjugate, let me copy paste. Once you write the conjugate, the next step is clear. Only chance we have is to break the conjugate, right? Because it's a conjugate of a sum. So we can write like this, a difference of two conjugates. But then we can do this even finer, right? Because B, if we look at B, right, it's here, B is a real number because we are adding together the magnitudes, the modules of the Bj that are real numbers, the absolute values. So then we can just keep the modulus on the number that is actually complex, like purely complex, AJ. B is purely real. But then when we look at C, it is a complex number because here, did you notice here, this is a product of two complex numbers, then they are added together, so the result is complex. There is no absolute value involved here in the definition of C. Okay, so in this case, we can still break up the conjugation, but we need to keep C and Bj, both of them conjugate. Okay. All right. So what do we do next? What we can do is compute this product. Okay, so we are going to have B square AJ square minus BC bar, the sum of AJ BJ bar. Okay, then minus BC, the sum of AJ bar BJ. Okay, and then plus the modulus of C squared sum of the BJ squared, J equal 1 to N. And here I'm missing, let me create some space. Here I'm missing the absolute values. All right. So let's look at what we have. So looking at the first one here, this is B squared times the sum of the AJ squared, J equal 1 to N. That is the definition of A, capital A squared. So let's write it down. Sorry, not a square, A, there we go. And another one is, when we look at the last one is B times the modulus of C squared. Okay, so only the middle part is left. So what can we do with this? Here we just realize that this complicated sum that we have here is C, and the other one is C bar. So either way, we have minus B times the modulus, the absolute value of C squared. Okay, so this appears twice. Okay, and now notice that we have the same quantity minus 2 times B times C squared plus BC squared. So when we put those two together, we get the negative BC squared. And let's look back at what we got. So here, we have proved that this complicated quantity that we basically made up is equal to B times BA minus C squared. But now you notice that this I have on the left is always non-negative. And I also know that B is non-negative. Okay, let me assume that B is strictly positive. If B is equal to 0, the proof is very easy. You do here, you just go back to, sorry about that, go back to the beginning. Okay. So if we assume that B is bigger than 0, then BA minus C squared bigger or equal than 0, and that means C squared less or equal than BA. And if we put what is what, right, the definitions here, okay, we have the inequality we wanted. Okay, we have the Schwarz inequality. This is C absolute value squared. There we go. Less or equal than A times B. And we are done. Okay, this is the end of the proof. Now I have a question for you. You can think about what is the case of equality in this inequality. Okay, you can think about it geometrically with what we were saying about projections. Okay, that's also a problem in the homework.